Hello students. Uh, Today we'll discuss about kinematic indeterminacy and its application in the matrix development. Uh, in this lecture we are going to discuss how to calculate basically how we calculate the kinematic indeterminacy of any structure, whether it is a beam, it is a frame, or it is a truss. Then later we'll discuss few basics about the matrix development, how we generate a matrix, and what are the principal coordinate system and all into this lecture. So let us start. Uh, First of all, what is the definition of a kinematic indeterminacy? The degree of kinematic indeterminacy is also represented as dki, that is degree of kinematic indeterminacy. It is the minimum number of movements, or simply we can say it is a minimum number of movement or a degree of freedom with which the kinematic configuration of overall structure can be defined. That is the number of unknown independent movements of a structure. So basically kinematic indeterminacy is the number of ways a structure can move. It is a number of ways a structure can respond. It is a number of ways a structure can freely uh, movable. So it can be simply called as a degree of freedom. So sometimes we say calculate the degree of freedom, then it simply means the to calculate the kinematic indeterminacy of a structure. It is also denoted by dk, uh, also called degree of freedom. Kinematic indeterminacy, the number of unknown joints is called a degree of freedom. Number of unknown joint displacements is called a degree of freedom. Next is simple formula for degree of freedom in case of a beam is, for a beam, it is dk is equals to 3j minus e minus m. So basically dk is a degree of kinematic indeterminacy. Here j is the number of joints, e is simply the number of internal reactions, and m is the number of members. So basically, for beams, generally axial deformation is always neglected. What is axial deformation? Axial deformation is a deformation of a member along the axis. So in case of beams, generally axial deformation is not, uh, we do not consider axial deformation. Hence, the formula becomes like this. But if we are asked to consider axial deformation, then the formula, then this m will be eliminated from this formula, and the degree of freedom for a beam in case of axial deformation is considered becomes dk is equals to 3j minus e, and e is simply the number of internal reactions in the beam. That will totally depend upon the support condition. Now this is only for a beam. Here are a few more examples of a beam. This is a cantilever beam, and in this, if axial deformation is considered, then the formula is 3j minus r. 3j minus r if it is considered. Here you can see, if axial deformation is considered, it was 3j minus r or e. We can see anything. We just need to understand the term e or r is representing the number of internal reaction. So simply, if axial deformation is considered, it is simple 3j minus e, and if it is neglected, then 3j minus e minus m. So here it is 3j minus e. 3j number of joints are 1 and 2, okay, and r or e, it is 3. How? At the fixed end, number of internal reactions will be 3, so it is 3j minus e, that is 3. And if it is neglected, the number of members will also be counted, then it will be 3j minus e minus m. Number of member is 1. Here only member is this one, so it will be 3j minus r minus 1, that is 2. The other case, uh, in this case, it is 3j minus r. It is at a hinge support. There is the number of internal reaction at the hinge support is 2, and one is over here due to prop. So it is 3j minus r r. And r is 2 here and 1 here. That is 3. That is equals to 3. And if the axial deformation is neglected, then one member will be minus from this equation, because there is only one member. So 3j minus r minus M will give the value of 2. Similarly, it is a case of a propped cantilever beam in which this is a fixed support and this is a roller support. At the fixed support, it is 3j minus r. Uh, Here it is 3. At the roller, it is 1. Then it is 3j minus 4 is equals to 2. Similarly, if it is neglected, if the axial deformation is neglected, then it will become 3j minus r minus m. M is the number of member. Here also, it is only one member. In this case, if we see, this is a beam which is fixed at both the ends, and a roller support or an intermediate roller support is at the middle of the beam. In this case also, the number of uh, uh, total reaction is over here is 3. It is here is 3. It is here is 1. So total number of reaction is 7. See, it is 7. 3 into 3 minus 7, that is 2. And if it is the deformation is neglected, then the number of members will become 1, and it is 2. So 3 into 3 minus 7 minus it will be here. Just a second. Here it is 3 multiplied by 3 minus 7 minus 2. So it will become uh, 0. Okay. In this case, it is number of members are 1, 2, and 3. And so total number of reaction are 3 over here. 1, 1, 1, that is total 5. So 3 multiplied by 4 minus 5, that is number of joints are 1, 2, 3, 4. So it is 4. 3 multiplied 3j minus r. 3 multiplied by 4 minus r. R is 5. That is equals to 7. If axial deformation is neglected, then members will be subtracted from this equation. The number of members are 1, 2, and 3. So it is minus 3. That is become equals to 4. Now in this case, this is a fixed beam, fixed end. This is a roller, again roller. Number of members here 1, 2, 3. Number of joints are 1, 2, 3, 4. 4 number of joints. Okay, 3 multiplied by 4 minus 5. 5 is what? 5 is the number of reaction. 3 over here and 1 over here, 1 over here. So it is 5. 3j minus r, that is 7. And if neglected, number of members, there are 3 number of members, that is subtracted from this equation, and the value becomes 4. So this is how we calculate the kinematic indeterminacy of a beam. Simply, there are two ways. Generally, we do not consider axial deformation in case of a beam. We usually neglect it. But if we are asked to consider axial deformation, we'll simply subtract the number of members from the beam, and we'll get the value of kinematic indeterminacy. Now, this is in the previous slide, we have studied how to calculate the kinematic indeterminacy for beams. The formula was simple. That was 3j minus r minus m. But here we'll calculate calculate how to uh, we'll see how to calculate the kinematic indeterminacy in case of rigid jointed frames. For rigid jointed frames, generally axial deformation is neglected because the joints are rigid, that do not allow the deformation in either of the ways. So in case of rigid jointed frames, axial deformation is neglected, and we know if axial deformation is neglected, then the members will be considered and it will be subtracted from the equation. The equation of a plane frame becomes like dk is equals to 3j minus r or e minus m, and for a space frame it becomes 6j minus e minus m. So if we consider this frame, in this frame, total number of reactions are 3 over here, 3 over here. That is 3, 3. That is this equation becomes, and the number of joints are 1, 2, 3, 4. So let me write down. Number of joints, first of all, in this case are 4. Okay, so this is first joint, this is second joint, this is third joint, and this is fourth joint. Number of reactions are 3 over here and 3 over here. So the equation becomes like this. This is a case of a plane frame. The equation becomes like this. Equation is 3j minus e minus m. So 3 number of joints are 4. So that is 4 minus e. What is e? E is the number of reaction. There are 3 reaction over here and 3 reaction over here. So that is why it is 2 multiplied by 3 minus 3. 3 is the number of members. How many members are there? 1, 2, and 3. 3 members are here. So the degree of kinematic indeterminacy becomes 3. Hopefully, I think you would have understand this concept. You just need to remember this formula, that is 3j minus e minus m in case of a plane frame, and it will become 6j minus e minus m in case of a space frame. So one thing more, you need to remember that axial deformation is generally neglected in case of a rigid jointed frames. This is another example. In this case, total, I'll quickly, I'll not write down the formula again. It is a simple, you can see one more time, 3j minus e minus m for plane frame and 6j minus e minus m for a space frame. So number of joints here are 1, 2, 3, 4, 5, 6. 6 joints, 3 is into multiplied by 6 because it was 6j, 3j. So 3 multiplied by j, j is a number of joints and that is 6 over here. Minus e, e is a number of reaction, that is 3 over here, 2 over here, 2 over here. That is why it is 3 plus 2 plus 2. It is subtracted from this term, and minus m. M is the number of members. Number of members over here is 1, 2, 3, 4, 5. So it is minus 5. That is equals to 6. So this is a degree of kinematic indeterminacy. It can move in the 6 of the ways. That is first, second, third, fourth, 5, and 6. So these 6 is the number of coordinates selected, number of the ways the structure can deform, the number of ways the axial the structure can move. So that is simply a degree of freedom. The degree of freedom is 6 because this joint is having a degree of freedom 2. This is 1. This is 1. This is also 1. This is also 1. Okay. So in this case, simple case, all 4 joints are rigid. That is fixed. So total number of joints are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is why it is 3 multiplied by 12 minus R is 3 plus 3 plus 3 plus 3, that is 12. So R is 12, 3 multiplied by 12 minus 12 minus number of joints, number of members. So number of members over here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it is 14, minus 14, that is 10. So degree of freedom or degree of kinematic indeterminacy in this case is 10. Now this is a space frame, and for a space frame, we already know that the formula becomes 6j minus r minus m. So 6j minus r minus m will become like this. It is 6j, number of joints are 12, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So number of joints are 12. So it is 6j minus r. What is r? R is the number of internal reaction, and I already told you in the previous lectures also that the number of if a joint is rigid, then in 2D frame the number of internal reaction at each rigid joint is 3, and for a 3D frame it is 6. So 6 at each joint, 6 here, 6 here, 6 here, and 6 here. So it is 6 multiplied by 4 minus 16. 16 is the number of members. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, Now in this case, the total number of, first of all, we'll count the members. So total number of members over here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Total 16 members are here. Total number of joints in this case, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total number of joints are 12 in this case. The equation is simple. We know it. Let me write down again. It is 6j minus r minus m. This is the degree of kinematic indeterminacy. So 6 multiplied by number of joints, that is 12, minus r number of reactions, in this case internal reaction. I told you for a space frame, if the end is fixed, the total number of reaction at each end will be 6. So 6 over here, 6 here, 6 here, and 6 here also. So it is 6 multiplied by 4, because of 4 joints are fixed, minus 16. 16 is again the number of members. See over here, it is minus 16, that is 32. The degree of kinematic indeterminacy in this case is 32. This is how we can calculate the degree of kinematic indeterminacy in case of space frame as well. But just one thing you need to remember in this case, that the degree of the internal reactions in case of a space frame at a rigid joint is 6 instead of 3 in the case of plane frame. So next is the degree of kinematic indeterminacy in case of a pin jointed frames. So in case of a pin jointed frames, the degree of kinematic indeterminacy will become is equals to 2j minus e, that is for a pin jointed plane frame, and 3j minus e for in case of a pin jointed space frame. Remember, in case of pin jointed frames, the axial deformation is always considered, so no member will be subtracted in this case. The equation becomes like this: 2j minus r, or we can say e, anything, in case of a pin jointed plane frame, and for a space frame it is 6j minus r or e in case of a space frame. So this is a truss. It is example of a pin jointed space frame. Here also we'll calculate the degree of kinematic indeterminacy. In this case, it will be 3 multiplied by joints. Sorry, 2 multiplied by joints, because it is a 2D frame or a plane frame. So equation will be 2j minus e. So number of joints here are 1, 2, 3, 4, 5, 6, 7, 8. So it is 2 multiplied by 8 minus 3. 3 is what? It is the number of internal reaction. Number of internal reaction here is 2 at this end and 1 is at this end. So it is 2 multiplied by 8, that is 16. 16 minus 3, that is 13. So degree of kinematic indeterminacy in this case is 13. Now again, another case of a pin jointed plane frame. This is an example of a pin jointed plane frame. In this case, we can see that here it is here it is the total degree. Here it is the total degree of internal total number of internal reactions. In this case over here is 1. Over here it is 2. Over here it is again 1. So the number of internal reaction in this case is 4. Number of joints over here is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the question is 2j minus r minus nothing will be minus. It is only 2j minus r because it is a 2D frame. So it is 2 multiplied by joints. Number of joints are 1, 2, 3, 4, 5, 6, 7, 8, 9 minus r. R is internal reaction, that is 3 plus 1, that is 4. So it is 14. So degree of kinematic indeterminacy or degree of freedom for the stress is 14. Now this is an example of space truss. Again here the question is not 2j minus 3. It will be, because it is a space frame, so it is 3j minus r. Again number of joints here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of joints are 12, so it is 3 multiplied by joints, that is 12 minus r. Now what is r? All the ends are hinged, and each end is, it is number of internal reaction is 2. So total it is 4. So it is 2 multiplied by 4, that is equals to 28. And this is the degree of internal indeterminacy in this case of degree of kinematic indeterminacy in this case of space frame. So basically we are only concerned with 3 cases, that is for a beam, for a rigid jointed plane frame or a space frame, and for a pin jointed plane frame or a space frame. Uh, Now we'll quickly see how we generate the flexibility equation. This is the flexibility equation, very important when we will do the analysis of any structure using the flexibility matrix method. Then in the later videos and the lectures, you will be learning about the flexibility matrix method. So over here, I would just like to give you the application of finding out the kinematic and static indeterminacy, which we have read in the past lectures also. In the flexibility matrix method, we depend upon the flexibility equation, and because in this method we are first of all the first step is to calculate the static indeterminacy. Then by the results we proceed further into the analysis using flexibility matrix method. As whereas in case of a stiffness matrix method, we calculate the kinematic indeterminacy and we proceed further for the calculation of the required forces like shear force, bending moment, and do the complete analysis of a structure. So for flexibility matrix method, we need to calculate static indeterminacy, and for stiffness matrix method, we need to calculate the kinematic indeterminacy. This is a simple equation of flexibility matrix. This is a delta matrix del, and the matrix del is complete set of each displacement coordinates. Say del 11, del 12, del 13, del 14. The first term is represented. It is like this. Uh, it is like this. That is del I j. So term I represent where the impact is seen, and the letter j represent where the coordinate direction where the load is applied. So if we say del 11, then we are simply required to calculate the deflection or the displacement of the first coordinate in the if the unit load is applied at the first coordinate itself. If we say del 1 2, then it is simply the value of I is 1 and the value of j will be 2. So we are saying the unit, if the unit load is applied at coordinate direction 2, and we are required to calculate the displacement in coordinate direction 1. Similarly, if we say del 1 3, it means the unit load is applied at coordinate direction 3, and we are required to find out the displacement of coordinate direction 1. Similarly, if we say del 2 1, then we are saying the unit load is applied to coordinate direction 1, and we are required to calculate the displacement of coordinate direction 2, and so on. So simply the second term, or the j, represent where the unit load is applied, and the first term I represent the where the we are seeing the impact, or where we are calculating the displacement in which coordinate direction. Well, this is all we. So we are able to understand the how we denote this term del ij. That is, if it is del 1 1, then we are required, the unit load is applied at in coordinate direction 1, and we are finding the displacement in coordinate direction 1 as well. So the matrix del is known as the flexibility matrix. The element del ij is the displacement in coordinate I due to unit force. That is what I told you, in a coordinate j, direction j. In this similar way, we can simply what we can do, we can calculate all these displacement components, that is del 1 1, del 1 2, del 1 3, del 1 4, and all, and we will simply put this value into this matrix, that is del, and by using the flexibility equation, we'll derive further in the upcoming slides, and we will be able to find out the displacements. So and I'm just going to give you a very brief overview of this thing. The remaining things will see the whole process of analyzing using flexibility as well as stiffness method in the upcoming lectures. Now it is if we are considering it, the displacement due to I to force F2, the total displacement will be given as if F is the force matrix, that is the force applied, that is all the forces applied will be a complete set, and it will be termed as matrix F. Delta is the total number of displacement occurred due to the movement of the joints or coordinate system, and it will be a set of complete all such displacements, and it will be termed as delta t, or delta simply. So this is what delta is equals to force multiplied by the displacement, sorry, the displacement component. So the all such components will be termed as delta t total, that is total. This is f1 del I1, f2 del I2, f3 del I3, and such all till del in fn, that will be delta I. All such equations will come into a complete set, and this will be termed into delta 1, delta 2, delta n. This is delta matrix over here. Then again we'll break the two matrices. This is delta 1 1, delta 1 2, delta 1 3, and this is f1, f2, fn, and this is delta 1, delta 2, and delta n. So this we can simply write down it as a del matrix. Write down this thing as a force matrix, and write down this thing uh, as a displacement matrix, that is delta matrix. So this is basically equation of flexibility equation, and we have derived this flexibility equation. In the next slide, we will quickly understand the stiffness equation. Similarly, as in the case of flexibility equation, all the term I and j same we'll see over here also. In this case also, I represent where we are seeing the displacement, and j represent where the unit load is actually applied. So delta k matrix represent the stiffness matrix. It is same as the flexibility matrix. The same way, instead of delta in case of sorry, del in case of flexibility, here it will be stiffness, that is k. So k1i multiplied by delta 1, and all such will be given as f1. This is f2, this is fn, and we will make this a set and put it to a matrix. Then the matrix will become delta k multiplied by delta sorry, that is matrix K multiplied by matrix delta will be equals to matrix F, that is force matrix. And this is a stiffness equation. Now, there is a relation between a stiffness and a flexibility. We'll quickly see this is a stiffness flexibility equation. Um, this is a stiffness equation. Um, this is a stiffness equation. We can write down over here by multiplying k inverse to both the direction, both the sides. We'll get the k inverse will be cancelled by this term k. It will become delta, and the k inverse is over here. We'll solve it further. We'll get this thing like this, and then again it can be further this k inverse, this f will be cancelled by this f, and the equation becomes delta matrix is the inverse of stiffness matrix. So by this relation we can simply see that flexibility is inverse of stiffness. Now and if we also see this in a very general way, that if any material is anything is flexible, then obviously it will be not rigid or not stiff. But it is if it is stiff, obviously it will not be flexible. Or if a material is having more stiffness, then obviously the flexibility will be reduced. And similarly, if the material is having more flexibility, then the stiffness will be reduced. So in generally, if also we can see that stiffness is somewhere inversely proportional to uh, the flexibility. So here we have derived that delta matrix, del matrix, that is flexibility matrix, is inverse of stiffness matrix. Hopefully, this lecture would have been given you a brief knowledge about calculating the kinematic indeterminacy, and you would have understand the concept of developing a matrix. In the upcoming lectures, we will be studying about more cases. So till then, thank you, class.